Log on, tune in, find out. Another good idea from Cambridge.
Here I'm glad I was able to make it. And yeah, my talk today is probably a little bit different. It focuses on weather prediction. Well, I'll be making an attempt to connect to problems that we see in climate prediction. So yeah, statistical post-processing for ensembles of numerical weather prediction models. And let me give you an overview of my seminar. I'll first say a few things about probabilistic weather forecasting using numerical weather prediction, NWP ensembles. I will then introduce methods for statistical post-processing of the output from the numerical models, namely Bayesian model averaging, BMA, and ensemble model output statistics, or non-homogeneous Gaussian regression, EMUS, NGR. Two brief case studies, BMA for forecasts of wind direction, a circular variable, and EMUS NGR for wind speed. I'd like to say a few things about what I think is a grand challenge in statistical post-processing for weather forecasting for this decade, in that we need most calibrated and sharp forecasts of spatio-temporal weather trajectories rather than just weather quantities at individual sites and an individual, a single prediction horizon, a brief summary, and some thoughts on weather prediction versus climate prediction. To begin with, a summary of weather forecasting using NWP ensembles. Let me try to get the pointer here. Numerical weather prediction models are based on deterministic simulation models, and everything essentially dates back to an amazing paper by Wilhelm Bjerknes in 1904. It's amazing. That paper was published, 106 years ago, and essentially weather forecasting, of course, there's a lot of sophisticated detail, but essentially the general principle was laid down by Bjerknes in 1904, which is exactly how it's being done today. And what is so nice is that Bjerknes' paper is perfectly readable. It is crystal clear, makes for exciting reading, and again, even though the paper was written 100 years ago, it still provides a wonderful introduction to numerical weather prediction. There's a system of essentially 6 partial differential equations. There's conservation of momentum, mass, energy, and entropy, and equation of state, and 6 variables, essentially 2 velocity components, density, pressure, temperature, and humidity. This is very much like climate forecasting models. Of course, the temporal scale is very different. The equations are discretized and run forward to obtain deterministic forecasts of future states of the atmosphere. And of course, everything hinges, and again, that is a major difference to climate forecasting. The viability of weather forecasting hinges on the availability of good initial conditions on a 4-dimensional, on a 3-dimensional grid, current state of the atmosphere. So we need on the order of 1 to 10 million inputs, and this is being done in real time using a method that is called data assimilation. Essentially, these are what is better known in statistics as geostatistical methods, Kriging method, but very sophisticated methods, and everything is in very high dimensionality and needs to be done in real time. So it's highly non-trivial and requires the use of supercomputers. Okay, a few words on probabilistic forecasting. Traditionally, weather forecasting has been, or maybe I should say had been, viewed as a deterministic problem. Even though there's major sources of uncertainty, and the 2 major sources of uncertainty are those in initial conditions. I just mentioned that we need initial conditions. These are supplied by data assimilation systems. But of course, we have an incomplete network of observations. There's measurement error, there are shortcomings in data assimilation methodologies, etc. This is one major source of uncertainty. The other is in the model formulation. We have an incomplete knowledge of physical processes. Many processes need to be parameterized, that is, they are not explicitly physically model, but just via some summary statistics, and this in particular applies to subgrid scale processes such as turbulence, etc., and of course with incomplete and inaccurate numerical schemes. Yeah, so there is considerable uncertainty in weather forecasting, as we know, and there's been a major shift of paradigms since the early 1990s. And let me quote Tim Palmer here, who wrote in 2000, although forecasters have traditionally viewed weather prediction as deterministic, a culture change towards probabilistic forecasting is in progress. That was a decade ago, and much of this culture change, I believe, it's fair to say that much of this has indeed happened since. Probabilistic forecasting aims at finding joint predictive probability distributions for future quantities or events, rather than just a single valued point forecast. So, yeah, trivial example, point forecast for tomorrow's temperature here at the Newton Institute could be, I don't know, -5 degrees. The low temperature -5 degrees. A probabilistic forecast could be a normal distribution with mean -5 degrees and with standard deviation, say 2.5 degrees. And yeah, I don't need to make a point here that probabilistic forecasts are, the key advantages that they allow for informed decision making. Also, they quantify the uncertainty in the forecast. When you talk about point forecasts, it is, well, it's not entirely trivial to assess the quality of point forecasts, but it's even more non-trivial to assess the quality of probabilistic forecasts, if only for a single reason, in that our forecast is a probability distribution. When we're realizing low temperature tomorrow, of course, it's not a probability distribution, it is a single real number, so we need to compare apples and oranges when we want to assess probabilistic forecasts. And yeah, so we need to think about principles for evaluating probabilistic forecasts before developing methodology for doing this. We need to be able to assess how well we do. We need to be able to compare competing methods for probabilistic forecasting. There is an anecdote, a story behind this paper, in that we got to work on probabilistic forecasting some probably 7 to 8 years ago now. And I recall I was attending a workshop on forecast verification at the National Center for Atmospheric Research in Boulder, Colorado. And that was an exciting conference. I learned a lot at that conference. And as part of the meeting, we split into smaller groups. And one of those groups was on the evaluation of ensemble forecasts and probabilistic forecasts. And at the time, I was entirely new to the field. And naively, I was one of 2 statisticians, one of 20 atmospheric scientists. And possibly naively, at the beginning of that working group meeting, I asked, what do you think? What is the goal of probabilistic forecasting? What do we want to achieve? And I thought I'd get all sorts of sophisticated answers about the goal of probabilistic forecasting, but as it turns out, I did not get any answer. And that eventually led us to the 2007 paper, in which we contend that the goal of probabilistic forecasting is to maximize the sharpness of a predictive distribution subject to calibration. I should say a little bit about this, in that a natural answer to, well, what do you want in probabilistic forecasting is, well, I want to quantify the uncertainty and I want to find the true predictive distribution. But there is an operational problem with this, because the true predictive distribution, well, what is the true predictive distribution? Technically, the true predictive distribution is conditional on our current knowledge. If we want to make a forecast into the future, it's conditional on our current knowledge. But what is our current knowledge? Your current knowledge might be much larger than mine. Technically, we need to condition on sigma algebras. But this is, in my opinion, this is, in many contexts, this cannot be operationalized. And so we came up with this simple principle of maximizing the sharpness of a predictive distribution subject to calibration. Let me say a bit more on calibration and sharpness. Calibration refers to the statistical compatibility between the predictive distributions and the observations. So obviously this is a joint property of the forecasts and the observations. Put simply, if you predict something to happen with probability p, and repeat the forecasting exercise, in weather forecasting this is easy, unfortunately not in climate forecasting, but in weather forecasting we can apply our procedure day over day, and then events that we predicted to happen with probability p, if we look at the empirical frequency of those happening, well, that should be p. That is one aspect of calibration. Another aspect, or well, a closely related aspect, is essentially what we want the observations to look like random numbers drawn from our predictive distributions, from our probabilistic forecasts. There's many aspects to calibrations, but these are two facets that I think are useful. Okay, so we want calibration, and subject to calibration, we wish to maximize the sharpness of a predictive distribution. And sharpness refers to the spread of a predictive distribution. Think of that normal distribution, the forecast for tomorrow's temperature. I mentioned a standard deviation of 2.5. If we could issue a predictive distribution, a normal distribution, with standard deviation 1 degree only, and it were still calibrated, then of course we'd be happier. So the more concentrated the density forecast, the sharper, and the sharper the better, but always under the constraint of calibration. There's tools for assessing calibration and sharpness in the case studies. We'll get to this. And then there's proper scoring rules, such as the logarithmic score or the continuous rank probability score, and those allow for a joint assessment of calibration and sharpness.
Just a brief interjection at this point. What you've done here is really, if I understand you correctly, is you've tried to contain the problem of assessing the quality of a prediction entirely within the statistical aspects of the prediction. And you've not considered the role of the probabilistic information passing down the chain into a decision analysis. Because clearly,
yes,
if there was a contingent decision, we wouldn't do it like this.
Absolutely. So this here is in a general context independently of the application at hand. Yes, and that is, just imagine, for instance, the ECMWF, Rubensort for medium range weather forecasting. They produce raw forecasts that are then passed on to users throughout Europe for all sorts of purposes. And if you want to assess the quality of such forecasts, what weights do you give to users? We need some general principles. So this is the general situation in which there is no specific application at hand. If there is a specific purpose and application at hand, absolutely. Yes, we need to come up with methods that take the specific application into account. And actually, this can be done. So if you have a specific task, you derive the optimal decision from a predictive distribution, essentially the base rule. You act according to a base rule, and then say this results in a certain financial loss or reward. That actually is a special case of a proper scoring rule. So these more tailored methods of evaluating forecasts are in some sense, they can be subsumed in the framework here.
I think, and also what you're going to do is you're going to make an implicit judgment, I expect, that some aspects of the weather prediction are more valuable to users than others, and maybe focus on things like temperature and precipitation, and not worry so much about humidity and pressure. Would that be fair, or are you going to apply your scoring rules across the entire range of model outputs?
Well, you can apply them to each variable individually. And actually that's sometimes the case when you compare competing models or methodology, that one performs better for temperature, the other performs better for precipitation. If you need to come up with an overall assessment, of course, that is more of a management question. We can provide the tools, and this is what this and the next two slides are. But of course, you're right. We can't answer the management question. We can help answering them. We can provide the tools, but we can't answer them on behalf of users and managers. So let me say a few words about proper scoring rules. So a scoring rule is a function of two arguments. The first is a predictive distribution, f, and the second is a verifying observation. And you can think of this very general. So x need not be real valued, x could be very high dimensional, x could be a circular variable, whatever. And f is a predictive distribution that lives on the appropriate space. Okay, so we take these scoring rules to be negatively oriented, so the smaller the better. Now, proper scoring rule satisfies the following expectation inequality. F is a probabilistic forecast, a predictive distribution. Think of F, F like forecast, and think of G like genuine. So what does this, so this expectation inequality needs to hold for all probability distributions f and g. And what does it mean? If the future quantity x is distributed like g, so g is a genuine distribution, then if we want to minimize the expected score, of course the expectation is under g, under the genuine distribution of x. Now this expectation inequality says that if we want to minimize the expected score, then the best that we can do is to actually issue that probabilistic forecast, that predictive distribution G, rather than any other F. And so this encourages honest and careful assessments by the forecaster, because if the forecaster believes that X is distributed as G, then the best that she can do is to actually issue that forecast G and not hedge and use any other F. There is some interesting and nice theory. Proper scoring rules relate to convex analysis and information theory. Change the battery on that mic. Okay, thanks. New battery. So I'd like to give two examples of proper scoring rules. The first one is very well known. This is the logarithmic score, or negative predictive likelihood minus the log of the predictive density f evaluated at the verifying observation. And this is proper. This is just the Tilmann-Gneiting inequality, and this is what is being exploited all the time. For instance, Wald's classical proof of consistency of a maximum likelihood estimate actually can be very easily generalized to estimators that depend on an arbitrary proper scoring rule. The argument there really depends on propriety rather than on likelihood. Okay, the score that I personally use the most often is the so-called continuous ranked probability score, which was brought up in the 1970s in psychology and management science, and it does the following. It takes the predictive CDF. Now think of this as a CDF, and maybe I can draw a picture. So this is for a real valued quantity, and our probabilistic forecast can be expressed in terms of a cumulative distribution function. So it goes from 0 to 1. This is our forecast. And of course the observation, well, the observation is just some value. Here we use an x. So what does the continuous rank probability score do? It looks at the difference. So the observation corresponds to this Heaviside or Dirac delta function. Now there is a difference between this Dirac delta and the predictive CDF. We square the difference. So here the difference. The difference, and then we integrate over all thresholds y. And what is quite interesting is that this integral here can be written, assuming that f has finite first moment, can be written as the difference of two expectations, and here x and x prime are independent random variables that both have cumulative distribution function f. And what we can see here in this second form, so this is the random variable x, this is the observation little x. These all take the same unit as the observation. And what we see from this is that the CRPS, and that I believe is quite nice, that the CRPS comes in the same unit as the observation. If you're talking about temperature forecasting, the CRPS takes the unit of degrees Kelvin, degrees Celsius, and furthermore, if F is not a probabilistic forecast but a point forecast, then you see when this term here just becomes 0, and yeah, this random variable here attains a certain value, say y, with probability 1. So in the case of a point forecast, the CRPS just reduces to a mean absolute error, to the absolute error. So we have a direct, this is a score that allows for a direct comparison of deterministic of point forecasts and probabilistic forecasts, and this is something that I think is quite nice. Okay, and there's generalizations, but I don't want to go into these today. Okay, this was a bit of a detour on the evaluation of probabilistic forecasts. Now in the context of weather forecasting, how is it done in practice? It's done using ensembles of numerical weather prediction models. So each of these ensemble members, think of the order of 5 to 100, and each of these members is a single-valued deterministic forecast from an NWP model. But the forecasts differ from each other with respect to the two major sources of uncertainty, which are initial conditions and model uncertainty. This has been done in operationally since December 1992. Both the European Centre for Medium Range Weather Forecasting and the National Centre for Environmental Prediction in the US started global ensemble forecasting within 2 or 3 weeks of each other in December 1992. And then there's also, so these are global weather prediction models, when there is limited area systems such as the University of Washington Mesoscale Ensemble, which operates over Western North America and adjacent areas of the Pacific Ocean. And these have a considerably higher resolution, of course, and they operate at lead times up to 3 days, whereas the global systems typically operate at lead times up to 10 days. We developed much of the methods I'll be talking about on the basis of this UWME of the University of Washington Mesoscale Ensemble, and now in Heidelberg we are collaborating with the German Weather Service, German Weather Service has a Mesoscale Ensemble which is about to become operational, so it's in a testing phase, and hopefully we'll get real ensemble forecasts from them soon. Here's an illustration. So here we have Western North America, Oregon, US state of Oregon, Washington, Canadian province of British Columbia, and here the Pacific Ocean. And the UWME, it's an 8-member ensemble, and what you can see here is these are 8 forecasts of maximum wind speed 2 days ahead, valid August 7, 2003. And what you can see here is that the forecasts are similar to each other. They all run with the same model, but they come from different initial conditions. So they differ from each other, but we are similar, and the diversity among the ensemble gives us an idea of the uncertainty in the forecast. What do we see in such ensembles? Well, there's one very nice thing, and that is the spread error correlation. That is, there is a positive association between the ensemble range, that is the variability within the ensemble, and of course that's something that we know a priori, as soon as the forecast is attend, and the forecast errors. But of course the forecast errors, this is something that is known only a priori, and the forecast errors, they stand for the actual uncertainty in the forecast, and there is a positive statistical relationship between uncertainty a priori and the actual uncertainty in the forecast. And of course that is something very nice, and that is something that we can exploit. What is the bad? Well, these numerical models have biases that we need to and want to correct for, and they lack calibration. And in particular, they tend to be underdispersive, that is, they tend not to reflect the full range of uncertainty. The observed values, they fall far too often outside the ensemble range. So we have these model biases. These are errors in the first moment. And when you have a lack of calibration, essentially that is, you can think of this as an error in the second moment, and these provide a strong and well-recognized case for statistically post-processing these ensembles. And this is what we've been developing methods for. Again, the goal is to generate calibrated and sharp predictive distributions from the output of NWP ensembles. In particular, we want to address model biases and the lack of calibration. And yeah, there's a number of methods now, and the two that we have developed at the University of Washington and continue to develop now are Bayesian model averaging and ensemble model output statistics. And essentially, these are both methods address the same task, and we've developed them simultaneously in our groups, and essentially they perform very similarly. BMA is perhaps a more elegant method, a more general method. EMOS is a more parsimonious method, but in terms of actual performance, there's very little difference between these methods. Okay, but the kind of general approach is different. In BMA, we associate each ensemble member with a kernel function. It's like kernel dressing in density estimation. And when we give weights to these kernels and take the corresponding mixture distribution as a predictive distribution. And yeah, obviously if a member in the ensemble has a high skill, then the respective kernel tends to get a higher weight. Ensemble model output statistics is here the focus is somewhat different in that we do not fit a mixture model, we fit a single parametric predictive PDF, and that parametric PDF might have a certain mean. We fit that mean using summary statistics from the ensemble and over variance using summary statistics from the ensemble.
Well, BMA, when you say a weight reflecting the member's relative skill, you can obviously do that on one ensemble, one forecast, but then how do you say if you're doing the next time, which member of your ensemble relates to the best one the first time? Maybe it's to do with what initial state delay or something you're working with each time.
Yeah, very good point. So obviously, member's relative skill is of course relative to a training period.
You have to identify the member.
You have to identify the member, and so for this University of Washington mesoscale ensemble, the members are clearly identifiable because there's 8 members, and so there's 8 distinct initial conditions, and those come from different weather centers. For instance, there's a member with initial conditions that come from the Taiwanese Weather Bureau. Yeah. There's another one with initial conditions that come from the Australian Weather Bureau. So these are clearly identifiable. But when there's ensembles where members are not identifiable, such as the ECMWF ensemble or the NSEP ensemble, in those cases, all you can do is to treat the members exchangeably. So to give them the same weights, and which of course simplifies everything, makes life simpler. And so you really need to match the details of both methodologies. This concerns BMA as well as EMOS. You need to match the specific statistical model that you use to your sample. Yes, absolutely. And we developed these methods initially for the UW-ME. So the initial model formulation is for ensembles with non-exchangeable members, but we subsequently, in some sense it's trivial to adapt everything to exchangeable members because you use equal weights, etc. You use a single set of shape parameters, etc. But nevertheless, we have a recent paper where we describe all these adaptations and explain in detail how to apply them to ensembles with exchangeable members.
Yeah, but doesn't that depend on how you generate the ensemble? I mean,
absolutely.
If you generate the ensemble by having, like, perturbing some distribution, you have an a priori distribution you could put into that.
So again, the way that the European Centre for Medium-Range Weather Forecasting operates, and NSEP in the US, there's no choice but to treat the members. You have to treat the members exchangeably. Then there is the third major global ensemble, is the Canadian, and where actually it's debatable whether or not you should be treating the ensemble members as exchangeable. And there's a similar situation actually for the German mesoscale ensemble that is being developed. Over time, these ensemble systems, the way they are generated, have become more and more complex. And there's a continued need to think about what ensemble members you can treat as exchangeable and not. We now also have, for instance, for the Canadian ensemble, it might be possible to identify two groups. Essentially, it's a multi-model ensemble with two different models, and then some physics perturbations and initial condition perturbations within these two different models. So at some stage it might be of interest to apply BMA or EMOS model with two exchangeable groups. And all this can be done, but we need to gain more experience in doing this.
Because the weather centers themselves have addressed the issue of under-dispersion by tending to perturb along the directions of the fastest growing modes.
Yes.
So
Yeah.
this is not in any sense a random ensemble.
No, not at all. Not at all. Not at all. And you're right. It's what also all these things depend on the prediction horizon. So these random perturbations are we are directed at the errors at relatively short prediction horizons. And so things might also depend on the prediction horizon. Yes, yeah, no. The ensembles are very far from what we would consider a simple random sample. Very far from that, absolutely.
So am I right in thinking you'll be updating the weights as time goes on?
Yes. So what we do in practice is we use typically a 30 to 40 day window. So we use training data from the past 30 to 40 days, and then simply slide that training window ahead. Yeah.
So does that mean you get an idea of which members are better?
Yes, and actually that might depend on the season. And one important reason for using the sliding window training is that this is one way, this is a very cheap way of addressing seasonal effects.
You see that, you'll find that you might swap from Taiwan to Australia.
Yes. There are seasonal differences. Kind of for the future, what one might consider is not using just the past 30 days, but also use training data from the same season a year before or 2 years before. This is desirable, but it's not as easy as it seems. And the reason is that these ensemble systems are constantly being developed. So last year's ensemble might be, in several aspects, might be different from this year's ensemble. And that is actually, for that reason, what Tom Hamill has been proposing is reforecasting, that one should reforecast previous years with the current ensemble system. And of course, if the resources are there, that's a great thing. And that will really help us getting this. Yeah, this way we will get better training data and we can improve our predictions. But of course, it's a considerable effort, and the resources need to be there. Perhaps one interesting facet here is that the second method, we call it ensemble model output statistics. It's essentially a regression technique. It's heterogeneous regression. And we called it ensemble model output statistics because, model output statistics is the atmospheric science term for multiple linear regression. And then actually Dan Wilkes, atmospheric scientist, renamed it non-homogeneous Gaussian regression using the statistics term. So now there's both terms for the method. Let me go through this briefly. These are some of the implementation details. So here we ensemble forecast is x1 up to xm, m members. For surface temperature, in surface temperature, the BMA model is just it's a Gaussian mixture model. So here these are the original ensemble forecasts. We need to bias correct them when we have a certain variance sigma square here, and we have those BMA weights W sub I that reflect past performance. So the BMA predicted distribution is a Gaussian mixture, whereas the EMOS NGR, that's just a single Gaussian, and the mean of that Gaussian is a regression mean. We enforce non-negativity here mainly for reasons of interpretability, and also the variance is a linear function of the ensemble, of the variance within the ensemble. Yeah, in terms of predictive performance, about equal. BMA is more flexible. For instance, we can get bimodal predictive distributions from this, which we can't from even EMOS, but in reality, it happens very rarely nowadays that even with BMA that we get bimodal predictive distributions. BMA, initially, the initial formulation was with Gaussian mixtures for temperature and pressure. We also have an implementation for quantitative precipitation. Of course, that's a very different type of variable. For quantitative precipitation, we need to consider the probability of there being no precipitation at all. That is, there's always a point mass at 0, and then a continuous component for positive precipitation accumulation. So the BMA currents here are mixtures. We are Bernoulli gamma mixtures of a point mass at 0 and a power transformed gamma density. And very recently a similar model also McLean developed in the context of his PhD at the University of Washington for wind, and I just mentioned that there are ensembles with exchangeable members, and this table describes how the situation can be handled. Okay, I already mentioned there's an implementation for wind speed, and also for wind direction. For wind direction, this is a circular quantity, so here the individual kernels, they are von Mises densities on the circle. We've developed an R package named Ensemble BMA, and so there is software available for doing this, and if you're interested in probabilistic temperature and quantitative precipitation forecasts in real time using the UWME ensemble system and BMA post-processing, there is this website, propcast.washington.edu. Unfortunately, it covers the Pacific Northwest only. So these are the UK, not Germany. It's a very useful tool, actually. I think we used it a lot in a project, even for things like weekend planning. Where should we go hiking? Should we go hiking at all? But the project website once also made it on the title page of Seattle Times, and there are very many users in the general public that find this quite a useful website.
So if you're using it to plan your trips, that must mean that it's a proper scoring rule, right? Must be a proper scoring rule that you're using if you're using it to plan your trip.
Yes, if I had a well-defined loss function for a rain hike, yes, that would translate into a proper scoring rule. Yes, yeah. Okay, when the alternative methods EMOS, this was also initially developed for temperature and pressure. That is the simplest case because the forecast errors for temperature and pressure are to a very good degree of approximation. We are Gaussian. We have an implementation for wind speed, where the predictive distribution is truncated normal, truncated at 0, and there's also an R package, but that is not available yet. That is developed by Bob Ewan, and hopefully, will become available soon. An important point is locally adaptive estimation in heterogeneous terrain. Think of ocean versus lowlands versus mountains, upwind versus downwind, etc. It is really important to fit the respective statistical models locally adaptively, so that we have those various parameters. So if we go back, for instance, for BMA, we have these bias correction parameters. Quite obvious that these are not constant spatially. Also, that variance, the predicted variance sigma squared, is unlikely to be spatially constant. The weights are probably, well, at least empirically, there isn't much gain in spatially varying the weights, but there is quite a bit of gain in allowing the bias correction coefficients and the predictive variance to vary spatially. And the question is how to do this, how to estimate these models locally. Initially, we estimated these models regionally over the Pacific Northwest. And when you do this locally, there is quite a bit of additional problems. For instance, think of precipitation. If you're in an area in eastern Washington, essentially desert, where there is no rain at all for 2 months, how do you fit these respective parameters for probability of precipitation if there is no precipitation at all in the training data? So if you go from regional to local estimation, you essentially can't do without Bayesian regularization. So this is what we've been using initially for temperature. This is now coming up in monthly weather review, and Will Kleiber has extended this to quantitative precipitation as well. And again, here we need more sophisticated estimation methods, and particularly we need Bayesian regularization. 2 brief case studies, just to show these techniques in practice. I've chosen here wind direction. Wind direction is not as important as temperature precipitation, of course, but it's from a statistical point of view, it's interesting because it's a circular variable. And so the first question is, how do you do bias correction for a circular variable? We tried all sorts of things, and the meteorological literature essentially says it's impossible. Eventually, we used the latest circular regression methods, and with these it's possible. It's still disappointing. We reduce forecast error significantly, but not to the extent. Circular geometry is somehow strange. There's huge errors in the original forecasts, and we can only correct for a relatively small part of them. But at least we are quite happy that we can do a reasonable bias correction. But for some reason, that must have something to do with circular geometry. The effect is not as strong as everyone would like to be. So we first apply a bias correction using state-of-the-art circular regression methods. And then for BMA, we use a mixture of von Mises densities that are, so the x bias are the original forecasts from the ensemble, and then the bias corrected versions are the f bias. So it's like in the Gaussian mixture case, except that we've replaced the Gaussian components by von Mises components. Here we're using a sliding 28-day training period, and forecasts are 48 hours ahead. And here is an illustration. So this is at Castlegar, British Columbia. These are the original forecasts in degrees, and these are the bias corrected forecasts. And let's take a look at this. So here, this is the raw ensemble. This is bias corrected, and what you can see here is there is a slight shift, there is a slight counterclockwise shift. This is what bias correction does. So this is raw, and the bias corrected ensemble, this is for comparison a sort of climatological ensemble. And then here is the respective BMA mixture distribution, which of course is unimodal modal. And here, this is the verifying wind direction that realized. Also, you can see here that the weights for the 8 members are pretty much the same. And I'm not sure you can read this, but what you can see here is the CRPS. We're in the circle, so this is an analog of the CRPS, of a linear CRPS, the circular CRPS. And here we are, the CRPS values for the single forecast. Of course, in practice, one needs to average them over many cases to be meaningful. But we do see here quite a bit of improvement under post-processing. So here are performance results aggregated over Pacific Northwest. This is the circular CRPS. This is the circular absolute error, which is just the angular error. So it's quite high actually for a raw ensemble. an average angular error of more than 43 degrees. With bias correction, we get this down to 39. With BMA, actually, there is no improvement in the average circular, but that's not to be expected with BMA. The real improvement lies in the probabilistic metrics, so the circular CRPS actually is considerably improved by post-processing. Okay, turning to EMOS, NGR, and wind speed. I already mentioned the predictive distribution, the truncated normal distribution, with center a regression mean of the individual ensemble forecast, and variance. These terms you refer to the underlying normal distribution, so it's not quite a variance, but it's a spread parameter, being a linear function of the ensemble variance. Here we use a 40-day training period. Generally, results are really insensitive to the length of a training period. Typically, you need at least 20 days. And then kind of if you take training periods longer than 70 or 80 days, then seasonal effects kick in and you get a slight degradation. But whether you use 30 or 40 or 50 days really doesn't make any notable difference. Okay. So here is a specific example. This is at Vidal, Oregon, which is in the Columbia River Gorge. So actually wind speed forecasting is really important there because this is the windsurfing hub of Pacific Northwest. It's 200 kilometers inland, but it's a huge river, the Columbia River, and there is quite a bit of windsurfing there. Okay, what you can see here, it's an 8-member ensemble. So we have 8. These are the 8 ensemble values. These are the black lines here. And you can see the corresponding, one could call them EMOS weights. They're not really weights, they're essentially regression coefficients. And we can see that there is a very high coefficient here, and a considerable one here, and then there's essentially zeros for many of the other ensemble members. What you can also see is, so again, these are the ensemble values. This is the post-process predictive density, and you can see the post-process predictive density goes much further out to high wind speeds than does the raw ensemble. And yeah, this is one of the biases that I mentioned, in that the raw ensemble forecasts for wind speed we are generally much too low. And this is what statistical post-processing can correct for. So again, this is a post-process predictive density. This is the mean of a post-process predictive density. And what you can see here, this is I think it's an 80% prediction interval from the post-process predictive density. And this is the verifying wind speed. So in this case, post-processing did very, very well. In particular, it allowed us to compensate both for the low bias and for the lack of spread in the raw ensemble. Okay, here is an example. This is for July 1 to August 15, I think 2003. And what you can see here, the black dots, this is the raw ensemble. Then the gray, the box plot summarizes the post-process predictive distribution. This we want to compare to the ensemble. So we have an 8-member ensemble. So the range of that ensemble is it's an 80% prediction interval. So this is an 80% prediction interval, and the blue dot is the verifying observation. So nominally, both the ensemble and the post-process density forecast, so this box here is supposed to capture the observation 80% of the time. And if you check, we have the empirical coverage is very close to 80%, whereas if you look at the raw ensemble, the range of the raw ensemble captures the observation much less than 80% of the cases. And we see the effects here are reflected in the scores. So the mean absolute error of forecast of wind speed. So for raw ensemble 4.4 meters per second, and this is reduced by regional EMAs to 4 meters per second, by local EMAs to 3.6 meters per second. And again, regional and local means a general fit of the entire Pacific Northwest and a local fit directly at the station. And similarly, the CRPS is reduced by 20 to 30%.
It's a naive question, I think, but why have you chosen to model direction and speed separately rather than modeling the vector?
Oh, it's an excellent question. We started off with wind speed, essentially because it's the most important variable. There's a lot of results in the context of wind farms and wind energy forecasting. So we started off with wind speed, and wind direction, actually that was a student project that turned out very nice and turned out to be a publishable paper, but that really was an aside only initially as a student project in a PhD level class. And you're right, one should also model the wind component simultaneously, and we have done this. That is the final chapter in McLean Slaughter's PhD thesis. Has not been published yet, and we also have a student at Heidelberg now in Nina Schuhen in her diploma thesis. So McLean has developed a BMA procedure for wind vectors, and Nina has been developing an EMOS method for wind vectors. Yes, so we should also be doing this for wind vectors, and we have been doing this, and we are not yet there. So it is possible that if you use methods that are specifically tailored to wind speed and wind direction, that these do better for those respective quantities than a method for wind vectors, but unfortunately I can't report the results of this comparison yet, but hopefully soon. Yeah. It's also possible that if you model the whole wind vector, when you reduce everything to wind speed and wind direction, that you do better when the methods that are tailored. So it's a purely empirical question. I don't think there's a theoretical answer. One just has to do a comparison over in repeated situations and check empirically what works better. But yes, we're working on this.
I guess with all your experience, this is an unnecessary comment. I mean, direction is a funny variable because if you have very small wind speed, then it really doesn't.
Yes,
mean much.
yes, absolutely, yeah. And actually, in results that I just showed, we've excluded all cases with low wind speeds. So we have I think it's 5 meters per second, 5 or 10 meters per second, and we only consider cases where, precisely for this reason. We don't want to be modeling and predicting wind direction when there is essentially no wind. Absolutely, yeah. And again, that is something when you model wind vectors, you don't need to exclude cases. So my gut feeling is that it is better to model wind vectors directly. But we need to complete that comparison. Okay, I think have we looked at this? This is a comparison in terms of MAE and CRPS, and this is now over the entire Pacific Northwest. And again, we see substantial improvements in mean absolute error and CRPS. And these are rank and PIT histograms. I guess most, if not all of you, are familiar with rank and PIT histograms. This is how a rank histogram looks for most raw ensembles. It's the rank of the observation relative to the ensemble members. So the observation falls way too often below the smallest ensemble value or above the highest ensemble value, and they have these U-shaped rank histograms, whereas after post-processing we get uniform PIT or rank histograms as desired, indicating calibration, or at least showing no evidence of miscalibration. Okay, this is what we've done over the past 7 or 8 years. What I sometimes call a grand challenge ahead. All these methods are for a single weather variable at a single site at a single prediction horizon. But for key applications such as air traffic control, ship routing, etc., we need calibrated probabilistic forecasts of entire weather trajectories both spatially and temporally. So we need calibrate and sharp ensemble forecasts of space-time trajectories of future weather. And given our current focus of single variables, this is what happens. So this is a raw ensemble. Think of temperature at, well, this is a summer day. Temperature at, London and Bristol. If it's going to be hot in London, then it's likely to be going to be hot at Bristol as well. But if you do univariate post-processing, as I've talked about now, you lose the dependent structure. So the methods that we've developed, they work very well. For instance, if you want to predict wind speed at Weddell for windsurfing purposes, fine. But if you want to do ship routing or air traffic control, well, these methods are not going to be very useful. So what we really need is, we need methods that yield physically realistic probabilistic forecasts of spatial temporal trajectories. We cannot allow our statistical post-processing to destroy those physical relationships that are present in the ensemble forecast. That does not make any sense. Here's another application that I haven't mentioned. Of course, flood management. Critically important. If we want to plan ahead and predict river levels, etc., we need to get the dependent structure of precipitation right, both spatially and temporally. Yeah, I have mentioned these other applications, air traffic control and ship routing. I will not be talking much, time is running out, but anyway, this is work that we haven't, that we are doing at this time in collaboration with the German Weather Service. We are looking at parametric and non-parametric. Essentially, this is exactly the copular setup. We have all the univariate distributions, gotten them right by statistical post-processing, but now we need to combine them. So this is exactly the copular setup. We're looking at parametric as well as non-parametric approaches for doing this. And one method that actually we have already worked on is spatial BMA. And the basic idea here is that we trace each ensemble member. Think of temperature forecasts. This is what spatial BMA was to develop. It's physically realistic, spatially or spatio-temporally correlated, simulated error fields, and combine them into a post-processed spatial BMA ensemble. So kind of this is the raw ensemble. Statistical post-processing BMA EMOS can correct the margins, but loses the multivariate dependent structure. And then with spatial BMA, gets us back to the proper to physically realistic dependent structures. And this is work that we did initially with Julia Gell, who was a postdoc at the University of Washington, and then with Veronica Barrocal, I think who many of you know, and she did her PhD on spatial BMA and related techniques. Yeah, this depends on advanced, and particularly for precipitation, actually, this has been done for temperature, not yet for precipitation, and we do need novel statistical methodology. Okay, let me close with a summary. The goal in probabilistic forecasting is to maximize the sharpness of a predictive distribution subject to calibration. In weather forecasting, this is done using ensembles, but these call for statistical post-processing to correct for errors in first and second moments. We developed two methods for doing this, BMA and EMOS NGR. We supply to individual weather variables at single locations and single look-ahead times. And the challenge for the next decade is now to develop, to apply copular methods, to apply spatial statistical methods to get physically consistent probabilistic forecast of spatio-temporal weather trajectories. Let me close with a few words on weather prediction versus climate prediction. Weather prediction, of course, it concerns snapshots of the state of the atmosphere. So we have a wealth of training data that we can use to fit these models, and I've shown examples of this. Climate prediction concerns the probability of frequency distribution of the state of the atmosphere. Very unfortunately, there's a dearth of training data. If we want to post-process climate ensembles, it is a much, much more difficult task. There is the emerging concept of seamless prediction. I'm sure you've had discussions about this here, which forges weather forecasting climate change studies into a single framework. There's two Bulletin of the American Med Society papers, one by Tim Palmer et al., a very recent one, just appeared a couple of weeks ago by Haselager et al., and various with Easy Earth website, which is a consortium of European atmospheric scientists who want to work on this concept of seamless prediction. Let me close here and thank you for your attention. Yes, Reg.
So thanks a lot for this. I'm actually a windsurfer. And I get very frustrated with WindGuru, the main website, because it runs on MM5, I think, throughout the world. It could be much improved. So if you can make a contribution there, that help my future vacations. But okay, to be more serious, I was really interested in the EMOS part. I wrote 2 papers using much simpler models, much simpler situations, which are stratospheric ozone in 2006 and ground level ozone in 2008. So these papers were about statistical post-processing, correcting biases, but identifying how you can attribute the bias to additional variables. So if you could correct, so you see this ensemble, if it's systematically lower than the forecast by a certain amount, but you can attribute that to say a physical quantity, that signal, then you can correct the entire set of the entire ensemble meaningfully. However, this was much simpler in my situation. We're talking about processes that don't evolve as fast as weather. It's more chemistry. So do you think that you could start to play the meteorologist here and detect or attribute the deficiencies in the predictions to certain variables that you can access yourself? And correct your predictions accordingly.
That is very interesting. So make sure to let me know after this about the
I don't know if
exact references. Yes, we have another project pending final confirmation of the funding, which is run with atmospheric scientists at the University of Bonn, and there we are looking at questions very similar to those that you mentioned. This is definitely something you're interested in. It might also relate to sort of regime changes. And in certain atmospheric regimes,
yes.
You have a certain type of bias. In other regimes, you have another type of bias. So if you could identify the regime, that would be very helpful. There is some initial work in that area as well, by Susan Quabish, I think, if I recall correctly, not by our group. So yes, definitely. Essentially, what we've done here is it's a first attempt. These are, in many ways, these are simple methods. So we started off with fitting them over a region only, rather than at individual sites. We looked at individual weather quantities at individual sites only, and there is a lot of room for improvement. Absolutely. It's, on the other hand, one has to keep in mind that this is real forecasting, and overfitting is harshly penalized. So where is this balance? On the one hand, it's clear that these things need to be improved. We need more sophisticated ways. On the other hand, as soon as you are even just a little bit too sophisticated, you're penalized right away in out of sample forecasting. So yeah, there's a lot to be done.
If you're interested in floods from rainfall or from winds on the sea, you want to be confident about the extremes and whether you don't want false forecast, but
Yes.
if there is a real danger,
Yes.
then you want to be able to forecast that. Would that affect the approach?
Absolutely. I just mentioned a new project where we are waiting. We'll hopefully get final approving for funding. And that is within the Volkswagen Foundation has an initiative to support research on extremes. And we hope to work on weather extremes in this context. So, of course, one avenue is to tailor these methods to extreme situations, but actually when thinking about this, and this is also, we can hopefully do this work within the project, I think from a theoretical point of view, there are limits to the predictability of extreme events. And these are intrinsic limits, essentially the very fact that these events are extreme events makes them even less predictable than we think. I think we can all agree that predicting extreme is difficult, but it seems to me that it is, even at a higher, more abstract level, it is close to being impossible. And now I shouldn't be, and I don't want to be discouraging, but essentially the point that I think needs to be realized is what the public often does is there is an extreme event like the current one, and I'm not sure whether this has been discussed in the media, but what happens is if there is an extreme event, then the public and the media look at the forecast with the knowledge after the fact that there has been an extreme event. And if you approach forecast verification that way, that is, if you condition on an extreme event having happened, then I believe, and we have initial mathematical evidence of this, that essentially even the most skilled forecaster is bound to look silly in the public's eye. And that is essentially a mathematical property of conditioning on extreme events under quite realistic probabilistic assumptions. And that's something to be kept in mind. And actually, having thought about this, I have a lot more sympathy with economic forecasters who fail to predict the current financial crisis. Maybe it's just an intrinsic law of probability that if you look at the forecasts after the effect, by conditioning on an extreme event having happened, that even the most reasonable forecasters are bound to look silly and to look like fools in the public's eye.
One of the reasons you don't get the joint distribution correct is that the forecasts you produce no longer satisfy the original equations.
Yes.
You've lost all the
Yes.
physical information.
Yes.
Now, putting all the physical information back in would be really difficult, but some is fairly simple. Like the relationship between pressure and wind is a fairly simple equation. Is it possible to build that sort of physical understanding into your methods?
We think so. We are currently looking, and this is a diploma thesis that is close to completion. We're looking at a way where it is very easy to get back to a rank order information from your ensemble and essentially import that rank order information from your ensemble back into the post-processed predictive distributions. That is a beautiful approach, and in initial results, it seems to work quite well and essentially restore the physical information that was present in the ensemble, restore that back into the post-processed distributions. And so in a completely, one of the nice aspects of this method is that it works in any dimension. It works in dimension 10 million. Of course, if you have a 10-member ensemble, you might have limited information about 10 million dimensions. But to the extent that it's present in the ensemble, yes, you can restore it. Yeah. But we need more work, obviously. That is not the final solution. But it's actually, it's more viable to restore that information when I had thought just 2 years ago. Just 2 years ago, I said, oh, this is such a difficult problem, and I will not experience its resolution anytime in the next 5 decades. But actually now I think that we can come up with reasonable solutions within the next few years. Yeah, but of course you have to do it, and you have to show results.
Just a very brief comment on the issue of weather versus climate prediction. And it's not disparaging to say that your approach is ad hoc and empirical.
No,
And
no,
it's
no,
driven-
it is
yeah,
absolutely.
It's driven by the presence
Yes.
of large amounts of calibration.
Yes,
Now, we
absolutely.
have to be clear that climate models at the moment cannot replicate climate over the instrumental period. They all do equally badly, but
Yeah.
usually in different ways.
Yeah.
And they can only hit the high level targets like northern hemisphere temperature after anomaly correction.
Mhm.
Okay? And there's no evidence at all to suggest that were they to be able to recreate features of current climate during the instrumental period, that those models that recreated those features better would have better predictability. No
Yes.
evidence for that. So everything that we have to do, I think, in climate prediction, which makes it very different from weather prediction, has to be driven by foundational understanding of the relationship between climate models and reality.
Yes.
And that's really why I think we've come at this problem from an entirely different direction.
Mhm.
We started by saying, what do climate scientists believe about the relationship between their climate simulators and reality? Because that really is the dominant source of information when you turn climate model output into climate predictions. And that, I think, is why climate prediction is fundamentally different from weather prediction, and why I can't see myself that there's benefit in thinking about a seamless transition from one to the other.
Mhm. Yeah. With lack of training or calibration data is really makes the problem inherently more difficult and inherently different.
But I think even if we had it, it wouldn't be informative.
Mhm.
I think that's the key point.
Mhm.
Yeah. Thank you again.
Thank you.